In our last video, we finalized everything we need to know to relate rectangular coordinates to cylindrical coordinates. And what I want to do now is I want to integrate this triple integral, but I want to use cylindrical coordinates, not rectangular coordinates. What's nice is our procedures for finding bounds isn't changed. We're still going to be drawing rays perpendicular to the axis of first integration through a region spanned by the previous two. So actually, to change this from rectangular to cylindrical, I need to draw the region, or actually understand the region in space first. So I'm going to reimagine, right, this triple integral in rectangular coordinates as a triple integral in cylindrical coordinates. But first, from the first set of bounds, I know that z is between z equals 0 and the plane z equals x. I know that x is always between 0 and then the right-hand side of the unit circle in the plane. And then finally, I know that y is between -1 and 1, so I'll get that whole circle. And so I need to think about the region in space, but I know I'm going to need to think about the projection in the xy plane as well. And so this is pretty easy, right? X equals 0 here, and x equals the square root of 1 minus y squared. Certainly the right-hand side of the unit circle. Put that together with drawing it from -1 to 1 in the y direction, and I get this region. So that's the region I've traditionally called R. That's really a projection. All right, so now I need to think about the plane z equals x, right? That's the bottom of my region is z equals 0. Well, the plane z equals x comes through and slices on an angle and hits the base right there. So I could imagine half a cylinder coming out, getting cut by the plane at z equals x, and I'm gonna get something that looks like a lemon wedge. And so let me try to draw that in space as best I can, which likely is not going to be very good, but we just need to understand what's going on here. So I'm first going to imagine spinning what I've drawn there kind of into the xy plane the way I usually would when I'm drawing something in space. And so I have a z-axis coming out of the xy plane here. The plane z equals x comes through and slices that way. And so I get a line there and draw a lemon wedge. All right, so imagine a back wall kind of coming up like this, curving around, and there's my lemon wedge. Where the top part of it there is the line z equals x, or excuse me, the plane z equals x, and then I have that nice lemon wedge. All right, so let's imagine setting this up in cylindrical coordinates. X squared plus y squared is now r squared. dz, dx, dy is now dz, r, dr, d theta. In a moment, this will become an r cubed. Okay, bounds in the z direction. So I need to shoot a ray through my volume B, right, through the region, parallel to the z-axis that's perpendicular to that. So I would come in, I'd hit the bottom of the wedge at z equals 0, and then I'm going to hit the top, which is z equals x, but I need that in cylindrical coordinates. Well, x is r cosine theta. So I go in at 0 and I exit at r cosine theta. Okay, so now I need to look at the region R, but I need to treat it like it's a polar region. And so I draw a ray in increasing direction of R. Well, I would start at the pole, travel through the region, and then exit at the circle, and that would be from 0 to 1. And then finally, I need bounds for theta that include the entire region. Well, I think if I start here and rotate around this way, I definitely get the entire region. And so that would be from minus pi over 2 until I get to pi halves. So I started with a rectangular integral, a rectangular triple integral. I drew, as best as I could, the region in space and the projection of the plane, and then I followed that same procedure that we've been following to find the bounds of my cylindrical coordinate triple integral. And now I'm ready to integrate. To give us enough room, I think I'm going to rewrite this on the next board. Going on and writing this down as an r cubed. All right, our bounds for theta were minus pi halves to pi halves. Our bounds for r were from 0 to 1. On z, we're going from 0 to r cosine theta. Our integrand is now r cubed, dz, dr, d theta. Well, antiderivative with respect to z, I would get z. So I have r cubed z evaluated from 0 to r cosine theta, dr, d theta. So now I evaluate and I get r to the fourth cosine theta. I plug in 0, I get out 0. Oop, I forgot the integral from 0 to 1 there, dr, d theta. Well, we're now ready to integrate with respect to r. We get 1/5 r to the fifth, evaluated from 0 to 1, cosine theta, and now just a d theta. Well, this evaluates very easy. I get 1/5 minus 0 is just 1/5, which I can write out front of the only remaining integral. And from here, we will just have 1/5 sine of theta, evaluated from minus pi halves to positive pi halves. Well, that's going to give me a 1/5 minus a minus 1/5, which is 2/5. And there's our nice, happy triple integral, having changed from rectangular coordinates to cylindrical coordinates.